let's move on to our next talk. Jillian, if you could share your screen, please. Perfect. So our next talk is also by a graduate student at Northwestern University, Jillian. Jillian, do you have the timer pinned as well?
Yes.
Perfect. So we see your screen, hear you. Go right ahead.
Okay, thank you. So hi, my name is Jillian Rastinejad. I'm a PhD student working with Wenfei Fong at Northwestern University. I first want to start out by saying thank you to the previous speakers, the feeling that they would set up why we want to search for Kilonovae and the required background for Kilonovae really well, which they did. I'm going to be talking about Kilonovae following short GRBs with Roman, which is a little bit different than looking at gravitational waves. And so my first few slides are actually about short GRB Kilonovae searches themselves and the advantages to doing them versus looking for Kilonovae in multi-messenger astronomy. So the first point is that the Swift telescope is very good at detecting well-localized short GRBs. So the primary reason for this is because along with your short GRB, a synchrotron afterglow is often detected all across the electromagnetic spectrum. And so in particular, Swift XRT localizes the X-ray afterglow promptly. And this is nearly always a less than 5 arcsecond localization. Of course, this doesn't always happen, but in many cases it does. And then indeed, we can follow it up with a slew of other telescopes across the electromagnetic spectrum, including radio telescopes and optical telescopes, which therein further localize the event. So this is just an example field of the short GRB of GRB 200522A. So one of the primary advantages to this great localization is that you're able to identify likely hosts and then possibly the photometric or spectroscopic redshift of that host if it's in the footprint of a large survey. So some surveys that we use currently are the Legacy Survey, SDSS. Looking forward, LSST and the Rubin Observatory will be really useful in getting these redshifts. But these can really give you an indication of what you would expect the luminosity of a short GRB kilonova to be right away, so you can start to trigger your telescopes and get those observations that you need. The second advantage, and the previous speaker set this up really well, is that indeed we do expect there to be diversity in the observed kilonovae depending on the viewing angle. However, the advantage to short GRB kilonova searches is that due to the detection of a short GRB, we can assume an approximately fixed viewing angle. Therein, we can say that any of the diversity that we observe is due to intrinsic properties of the kilonova itself, as we wouldn't really expect the kilonova to vary too much within the opening angle of the jet that we'd expect to see the short GRB for. And then finally, a major advantage is that there are decades of short GRB discoveries, well over 120 detected by Swift alone. And so these span a wide redshift range. The disadvantage to this wide redshift range is that if you want to detect a kilonova at these distances, you need deep imaging. However, we already have around 12 candidate kilonova detections. A large part of the reason why I say candidate kilonovae is because that afterglow that I mentioned earlier fades faster in the optical than a kilonova would, depending on your model, I guess. But disentangling that afterglow and kilonova emission is non-trivial, but that doesn't mean that there aren't some pretty, I guess, clear-cut cases of a kilonova detection. So this is showing the late time light curve of GRB 130603b. We see that there's this bright near infrared detection at late times at the same time that we have a very deep optical upper limit. And so as the previous speakers established, you would expect kilonovae to be red, especially at late times. And so this was the first announced case of kilonova. So moving on from there, another advantage to having the large sample is that it allows us to look for diversity in the observed kilonovae, so their colors and luminosities in particular. And so we are certainly not at the place where we can tie a photometric detection, just one of those, to our process production. However, looking at the diversity in observed short GRB kilonovae does give us some insight to the range of R process production per merger, tying into larger questions like are binary neutron star mergers the sole site of R process production, which I think that the next speaker will probably talk about some other possibilities. So getting on to the work that we published last year, what we did is built a comprehensive short GRB Kilonova catalog that includes optical near-infrared detections and deep upper limits of 85 bursts detected over the last 15 years. So this is the most comprehensive Kilonova catalog to date. And indeed, we include unpublished data from premier ground-based telescopes, including dear to my heart, the MMT, and then Gemini. In addition, we went through the GCNs for recent bursts and collected any data. And then finally, we did a literature search collecting relevant short GRB Kilonova observations. So one thing that I want to highlight is how our entire sample compares to AT 2017 GFO. So the 8 light curves of AT 2017 GFO are shown in the black lines in the R band on the top and then in the J band on the bottom. Analysis that we do in the paper is compared to a number of other fiducial models, including that of a neutron star black hole model, a stable neutron star remnant model, and then even a magnetar model. So those are the different colors, and you can look at the paper if you want to see our comparisons to those. But if I overlay the catalog, which is completely shifted to the rest frame in luminosity units, rest frame time, and then we blue shift the observations to the approximate rest frame filter. So now what's overlaid are deep upper limits as triangles. If they are unfilled, it means that we don't know the redshift of that short GRB, and we assume a redshift of 0.5. In addition, detections are overlaid as circles, and we can already begin to see the diversity in what's observed for kilonovae in the 2 bands. So what we want to do next is we want to compare across bands to examine the sample trends compared to AT 2017 GFO. So we take the ratio of the observation to the model. So this is showing the ratio on the y-axis and then the time on the x-axis. Different filters are overlaid in colors, and then we highlight Kilonova candidates as stars. So just giving the quick highlights, Kilonova candidates are more luminous, generally in bluer bands than 17 GFO. In addition, we find deep upper limits of 10 bursts, so 10 out of the 85 in our sample, that fall below the 1-to-1 ratio. So this 1-to-1 ratio denotes what the Kilonova of 17 GFO would fall along if it was plotted here. So overall, what this demonstrates is that rest frame optical Kilonova observations show a span around a factor of 100 in luminosity. The next thing that we do is we make ejecta mass and velocity strains for given electron fraction values. So we created grids of analytical models. In this plot on the left, each square represents a model parameterized by the ejecta mass and velocity. We overlay estimates of previous short GRB kilonovae and a suite of Kilonova model estimates. What we do is we iterate through each square in this grid and just simply in a binary way determine if that deep limit rules out the model or not. So this is for a relatively low electron fraction, as Jenny discussed. We also do this for a bluer component electron fraction, and then we also do it for a very blue component, just because a lot of our catalog is in the optical. So what hopefully is immediately obvious is that current short GRB observations are much better constraining of blue ejecta diversity more than red ejecta. So this certainly does not mean that there's less blue ejecta than red ejecta. It just means that our observations don't touch the red ejecta grid to the extent that they touch the blue ejecta grids. And then also we compared to the grid of models from Case et al. 2017, and we find that the ejecta mass and velocity constraints are certainly model dependent and can vary on the order of 1/10 of a solar mass. So now I think this point really leads into why we're here, which is to discuss the Roman Space Telescope. So I think it's fair to say that current observatories effectively probe nearby blue component short GRB kilonovae. And that leaves the Nancy Grace Roman Space Telescope to uniquely probe the diversity of red kilonova components. And so in short GRB kilonova follow-up, we really don't need to make use of the wide field of view, but what's really important to us is getting these depths in the near infrared. And I'll explain why in a second. We really can't do that with current observatories. So this is showing the filters and the wavelength coverage that they have. And then of course you can see these really incredible depths that Roman should be able to reach in imaging. Finally, I want to note that the TOO slew times, best I could find online, were that they promised within 2 weeks. But as I'll show in a second, this should be adequate for discovering and characterizing nearby short GRBs. So this is showing light curves in the optical on the left and then 3 near infrared bands. These are AT 2017 GFO light curves that are smoothed and then shifted to different redshifts. I want to note that the solid lines represent redshift 0.5, which is the median detected short GRB redshift. And then we also overlay typical depths of ground and space-based telescopes. So what this shows us is that current ground-based facilities can only observe nearby short GRBs in the optical. These timescales for the ground-based facilities point to likely afterglow contamination, so they're not the definitive kilonova detections we want. And then finally, I want to note that HST is a really powerful tool and has been in the past for following short GRB kilonovae, but realistically, we can only trigger on about 1 short GRB per year, and we don't have redder coverage than F160. So now overlaying the depths of Roman, as Jenny mentioned, it should be able to detect kilonovae out to a redshift of 0.8. And then synergies with other observatories might allow for multi-epoch observations in these redder bands, which is useful in constraining the ejecta mass and velocity properties. And then finally, this F213 filter will probe redder wavelengths than HST allows. It has comparably lower depths, but we can still certainly use it for lower redshift bursts. So I will leave my conclusions up here. Thank you very much, and thank you for having me.
Excellent. Thank you, Jillian. That was a great talk. Questions for Jillian? So I don't see anything in Slack or Zoom, but Jenny has a question.
I do have it. Well, yeah, Jillian, would you mind going back to the slide where you were comparing the blue emission? It was the one with the plot with the horizontal line that you said would be GW 170817. No, a few slides back. Sorry. I should have made a note of this. Okay. Yeah, okay. So I'm sort of fascinated by this argument that you have more luminous, so many kilonovae that are more luminous in the blue bands than 170817, just because 170817, the inferred mass was much higher than was expected for what we think of as these like blue emission producing outflows. I was wondering if you guys had any interpretation of that, or how we should think about these apparently very massive low YE outflows.
Yeah, thank you. That's a really interesting question. My first thought ties into the idea of the squeezed dynamical ejecta that comes out through the poles that would perhaps be bluer. Another thing that I'll say is that these are, again, kilonovae candidates. And so these don't seem to be likely afterglow behavior. However, it is entirely possible that there is some combination of afterglow that is still in here, contaminating them. So I think hopefully with future observations, whenever we see a relatively nearby kilonova now, we try to get both optical and near infrared. But when we look at these past observations, we really are biased towards the optical. So that's all we can see. So we don't know if it's just overall bluer or if it's just overall brighter, if that makes sense.
Yeah, thank you.
Okay. Any other questions for Jillian?
Eli has her hand up.
Sorry, Jillian, please go ahead. Yeah.
Thank you for that really interesting talk, Jillian. So my question, I'm not totally awake, so I'm not sure if you've already answered it, sorry, is that, so what kind of timescales are you able to do follow-up of these GRBs for? And yeah, so that's my question. So you get the GRB, what is the strategy to do follow-up and how fast can you get on them?
Yeah, that's a really good question. So the first thing that we do when we get a short GRB detection is we go look it up in SDSS Pan-STARRS legacy survey to try and see if there's a galaxy in the XRT region, and if so, what the photometric redshift is for that galaxy. And so that really informs how we want to approach our strategy. We do have programs on telescopes like Gemini and MMT, and I'm a co-I on a future JWST proposal to follow up a short GRB. But it all depends on what that redshift is, and that kind of informs our strategy of how we go about it. Because as you can see, as this plot shows, what the redshift is really determines how long your kilonova is going to be observable from the ground or even from a space-based telescope. So we want to make sure we're using those resources wisely.
Okay, thank you, Jillian. Let's continue this discussion on Slack.